Hello and welcome to today's webcast brought to you by Laser Focus World. Today's event, Considerations for Thin Film Deposition in Semiconductor Laser Manufacturing, will be presented by Alex Manison, Applications Development Manager, and he will be joined by David Douglas, Product Manager, both with Denton Vacuum. The presentation is both live and interactive, so you can ask questions at any time by typing your question into the Ask a Question box in the presentation window and clicking the Send button. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available for on-demand viewing within 24 hours of this live event. A reminder email message will be sent to all registrants with a direct link to the archive. It can also be reached from our homepage at Laser Focus World. If you have any technical difficulties, please also type your issue into the Ask a Question box, and a member of our support team will work with you to correct your issue. Now it gives me great pleasure to introduce Alex Manison. Alex?
Thank you very much, Tammy. Hello, everyone, and welcome to today's webinar on the considerations for thin film deposition in semiconductor laser manufacturing. As Tammy has mentioned, I'm from Denton Vacuum. We are in capital equipment manufacturing for deposition processes. We have been around for over 50 years and have been helping engineers, process engineers, and other engineers in developing semiconductor lasers since the beginning of the semiconductor laser manufacturing age. Our goals as a company are to improve manufacturing yields for our customers, to gain efficiency, throughput, and of course achieving repeatable performance over as wide a process window as possible. Before we begin, I would like to present you with the lead-in poll question to introduce the theme of the webinar. So hopefully you're seeing the question on your screen. Let me read it out loud. So ideally, when performing thin film deposition, what is the most important element that you're looking for? Is it the attributes of the tool, such as type of the sources, number of the sources, pumping system, process monitors, pump down time? Or is it the system performance, such as film properties, throughput, and uptime? So take a minute to answer the question, and then we'll give it some time and then proceed with the presentation. So let's keep going. Thank you for your feedback. Let's begin with a quick overview of the semiconductor laser market. The semiconductor laser market has been growing at a phenomenal rate over the past 20 years, with the diode lasers making up about 45%, with a total market cap of about $11 billion. All players as of right now, currently pursuing development more or less independently. But at some point, it will become impractical, expensive, and inefficient, as we have seen both in microelectronics industry over the past 30 years, the change that it has brought to LED industry over the past 10 years or so. As the laser industry has matured, the number of equipment vendors have developed deep process understanding across the industry, across multiple customers. So, by adopting some characteristics of the much larger and more experienced microelectronics semiconductor industry with a $50 billion market cap, the process engineers and device designers can try to adapt some of the industry best practices without really sharing the detailed proprietary process or design knowledge. So in this webinar, I'd like to examine how this idea of adapting some of the semi approaches to device manufacturing translates into actions by following key steps of the laser manufacturing process and taking slightly deeper dives into individual steps and what are the key considerations to consider. Here's an example of the laser bar manufacturing process flow. I just want to mention it's by no means definitive and can definitely vary substantially depending on the type of laser that you're using. Is it a VCSEL or an edge-emitting laser? Does it have internal cavities or external cavity, etc.? So this is just an example of the process flow, but it would have most of the key processing steps that you would see across all types of laser manufacturing processes. We start with the process of heteroepitaxy for the contact layers and the active layers. And looking a little bit more in the detail, we see just as much of variety in the active layer structure as in the devices themselves. We typically start with a substrate, silicon or silicon carbide, gallium arsenide, indium phosphide, sapphire. Variety is great. Often we do transition layers for stress control, and sometimes they can be short period superlattices. As an example of wide band gap laser diodes on gallium nitride, you would have aluminum gallium nitride and gallium nitride layers, followed by a buffer layer, which is typically either undoped or lightly undoped, and this would provide a native substrate for the active layers for your material system, such as gallium arsenide or indium phosphide or gallium nitride. Next, we move on to N-type contact layers, cladding layers for injection, waveguide, and then the prize layers, the active layers, which themselves have a great variety, starting from undoped maybe quantum well, single quantum well structures, to multiple quantum wells, to double hetero structures, and so on. And on top, we typically have the P-contact layers with waveguide and cladding. And this whole structure, again, is just a representative, but it's indicative of what we typically see in a laser diode. And that kind of completes our coverage of the active layers, and hopefully I haven't lost half the audience with this, but let's remember that active layers is not the entire diode, and what follows next is actually just as critical. So moving on, we see that the next step is typically photolithography, patterning, followed by etch to the desired depth to define our waveguides for the lasers and the diode mesas. Then we follow with the deposition of the dielectric material required for carrier confinement to the diode mesa. Afterwards, we'll need to open this dielectric layer with an etch and then deposit P metallization, so actual P contact, P metallization. And if needed, we do additional metallization, such as maybe electroplating for thicker, more sturdier contacts. Some processes follow with substrate thinning to less than 100 micron, maybe 70 to 90, or in some cases there is full substrate removal. Let's not forget the P contact is done. Now we're moving on to the N contacts, and that kind of finishes up our metallic layers. We do anneal, cleave them into bars, and are ready for pre-packaging. And typically this includes the facet coatings with anti-reflective and highly reflective coatings, depending on the diode structure, followed by the packaging where a final laser diode is produced. As you can see, our device manufacturing process flow has several deposition steps beyond active layers. Several deposition techniques are available to us, and this table illustrates some considerations that go into the technology selection. Let's start with the least technical, yet less important capital expenses, so the cost. For a laser diode with low let's just call them quote-unquote low technical requirements, meaning maybe low power laser bar, we would have thermal evaporation for metallization layers. Although they are fairly cheap, they can be sufficient in a lot of the cases. A slightly better technique, but slightly more expensive, would be e-beam evaporation, which gives you a broader range of available materials, slightly higher deposition rates, and possibly a little bit better film performance. If we need something, say for such a high power laser, some key properties that are more denser film, or for example, better adhesion, ability to withstand higher currents, we would go with a little bit higher cost options such as magnetron sputtering or even ion beam sputtering, which though is very, very expensive and complex. With after the cost considerations, we're moving to somewhat related, yield, which goes into the cost of ownership, and throughput. As you can see, there is also quite a differentiation here between different technologies. Although thermal resistive evaporation and e-beam evaporation by themselves on their own do not provide necessarily very high uniformity films, there are ways of achieving really excellent uniformities with planetary motion and masking, or in both cases. The scalability, on the other hand, the throughput, in both cases is limited. Of course, we can increase the chamber size for batch processing, but if we want to go to really high throughput, maybe magnetron sputtering would be a better choice, because magnetron sputtering with the automation for inline systems can be very high throughput with very excellent film quality. And mentioning the film quality, the elephant in the room, if this is the main consideration, such as really high power lasers, we would have to go with more expensive technologies where thermal evaporation and e-beam evaporation, even with ion assist, would not provide a sufficiently high quality material, and we would need to go to something like magnetron sputtering or even ion beam sputtering. Now that we've gone over the high-level overview of the technologies, let's do a slightly deeper dive into what we should care about when considering individual layers. We'll go over a few examples: the reflectivity coatings, so AR, HR, metallization layers, and the dielectric coatings. But before we begin, let's revisit our polling station. Today, when you specify thin film system, what are you actually focusing on? Are you focusing on the attributes of the tool, such as the type of sources, the number of sources, the pumping system, process monitors, pump downtime, or are you focusing on system performance, such as film properties, throughput, and uptime? Please take your time, give it about a minute to answer the questions. All right, let's move on. Let's start our examples with AR, HR coatings. What are the key considerations? AR coatings are anti-reflection coatings. Their purpose is to decrease the reflectivity of the facets through which light enters and exits the laser cavity. They're done in some cases with a single layer of appropriate refractive index material, or more often for high quality coating, they'll have alternating dual material high and low refractive index stacks. Typical materials used for these coatings are TiO2, SiO2 stacks. Sometimes TiO2 is replaced with tantalum pentoxide. And the key physical property of this film would be reflectivity, and the reflectivity should be in the range of 3 to 10%. On the other hand, we have highly reflective coatings, HR, and their purpose is to stop light emission from the rear facet of laser diode and to reflect most of the light back into the laser cavity. So while AR coating had a requirement of 3 to 10% reflectivity, the HR would have a greater than 90%, or in some cases greater than 99.9% reflectivity requirement for the physical properties. This is achieved also with alternating dune material, high, low, and stacks. And the typical materials are aluminum oxide, silicon, or zinc sulfide, TiO2, SiO2. There is a broad range of choices. When we look at our films, we can subdivide their properties into what we would like to call intrinsic film properties and extrinsic film properties. The intrinsic film properties have more to do with the physical properties of the films. In this case, in case of AR, HR coatings, it would be reflectivity, absorption, scattering, laser damage threshold. These qualities directly impact product performance, so your laser performance. They would depend on the material system selection, in the case of AR/HR, also on the optical stack design. They would depend on deposition technology selection, so what is the best quality you can achieve of the material for a particular technology. They also will be highly dependent, especially in the cases of very large number, high number multi-layer stack. They will highly depend on the process control, precision, and also deposition environment integrity, such as how good is your vacuum, how clean is your system. The extrinsic film properties are more related to the cost of ownership, and these are uniformity, repeatability, deposition rate, and throughput. They also depend on technology selections. Some technologies have high deposition rates, better throughput, but they also depend on the system design. If you're using planetary motion, you will get much higher yield, so your cost of ownership will obviously go down. They also depend on deposition system quality. Are you choosing the minimum pumping system, or are you going with a bigger pump so you can achieve a lower base pressure? And going from these examples, how do we translate our desired film properties into the process equipment selection? Let's examine the following scenario. We have an AR/HR layers for low power laser bars in a high volume manufacturing setting. These would translate into coating requirements of mostly related to cost, higher throughput, lower cost. Going down one step, the technology and configuration selection decision process would go something like this. First, we would identify the critical intrinsic and extrinsic film characteristics. This would be, we would need clearly sufficient adhesion for our layers. We would need minimal oxidation of the natively cleaved surfaces. And we also need low, keep the cost in mind. So how do these translate into the technology and configuration selection? So sufficient adhesion, we might need to use an ion source for better film adhesion. Minimal oxidation of natively cleaved surfaces, we can use something like a flip fixture. You see a picture below. A flip fixture would enable us to expose both sides of a two-dimensional substrate to the evaporant plume without really breaking vacuum. So there is minimal oxidation. Low cost on this, in this scenario would translate of choosing maybe E-beam evaporation over sputtering. And this is how we would go in this very brief example, go from the film properties into the technology and configuration selection decisions. Let's take another example of AR/HR coatings, just to contrast some of the selections we made in the previous slide. Let's go to a different scenario where the layers we're growing, AR/HR layers, are that we need for high power laser bars. The coating requirements here would be different. So the most significant, the most important ones would be tightly controlled optical properties of the film, and also the ability to withstand high laser damage. So how do these translate? How do we go through our decision process in this case? Again, starting with identification of critical intrinsic and extrinsic film characteristics, we would see that we would need excellent film adhesion, but we also need high density. We will need low defect density and low refractive index. So ion sources would address, in this case, most of our concerns. But going beyond that, we will need a very high number multi-layer film stack, especially if we want to achieve something like a 99.9 reflectivity HR coating. And for this, we might need a magnetron spotter source. We will also need high uniformity, so we'll need to optimize the geometry of the system and make sure that the throw distance and the source locations are optimal. And another critical, in this case, film property would be high repeatability of individual layers, so layer-to-layer control. So here we would have to have a sophisticated process control system, and maybe in this case it would be in situ optical monitoring system. And since we're touching on process control, let's briefly discuss our options, as they can be applied to most deposition technologies and can have a significant impact on both device quality and the cost. A more simple, lower cost, lower precision in situ control system would be a quartz crystal monitor. It provides information about the physical thickness of the deposited film. And while it may be sufficient for a lot of metallizations, it might be insufficient for some of the optical films. In this case, we would need to go to something more sophisticated, OMS. OMS is a real-time in situ system that measures optical properties of the deposited film. And here we can monitor either directly on film with a broadband monitoring filmer, so we can monitor the optical properties of our entire stack as it's grown in the system. Or we can have a kind of a witness crystal, which we monitor with a single wavelength optical monitor. We monitor the properties of an individual layer. Both of these types of control systems provide a more direct measurements of the film's defining characteristics, the optical properties. In both of these cases, they can be used as endpoint detectors. But in addition, since quartz crystal monitor also can be used as a endpoint detector, in addition, OMS can also provide and adjust for minor variations in the deposition rates and the operating conditions of the system, and resulting in more repeatable end products. So day to day, as you see your process drift over time, OMS can actually compensate on its own if properly configured. All of this higher precision obviously comes at a higher cost. So we have to keep in mind whether the quality is absolutely necessary for us to use the OMS versus QCM. Getting back to thin films, let's look at metallization and dielectric coatings. So what are the key considerations? Metallization layers provide low resistance with contact resistance of less than 10 to the minus 6 ohm centimeter squared, and also time-stable metal semiconductor ohmic contacts. The key physical characteristics would be low threshold voltage for the layers, low operating temperature, so our films do not heat up during operation, and also low metal diffusion depth. They're typically achieved with multi-layer metal stacks, with typical layers having wetting layer, a diffusion barrier, and a cap. And these are also preceded and followed by surface treatments. Typically, we see either chemical or plasma treatment, or both, of the oxides or contaminants prior to deposition of the metallic layer. And we typically see high temperature anneal after the deposition has been completed. Materials used for these layers vary widely. For gallium arsenide, the typical layer stack would be nickel, germanium gold, nickel gold for N contacts, and ti-platinum gold for P. For indium phosphide, we would have something like platinum germanium, or palladium zinc antimony palladium. Or for gallium nitride wideband semiconductor, we would have aluminum, so ti-aluminum, ti-gold for N layers, and platinum gold for P layers. Dielectric coatings, on the other hand, provide current confinement to active layers. So their key physical properties are highly resistive materials. They have to be highly resistive and have very high breakdown voltage. Typical technologies used for these layers are RF sputtering and reactive sputtering, while for metallization, we can use sputtering as well, but we can also use evaporation. Since we mentioned the process control, for reactive sputtering, you have another process control system, which is a plasma emission monitor, where you control the plasma during deposition. And it's a topic on its own that can be discussed at some other time. The typical materials used for dielectric layers are silicon oxide or nitride, and sometimes germanium cyanide. Going to intrinsic and extrinsic film properties. So for metals, these would be sheet resistance, contact resistance. For dielectrics, it would be resistivity and breakdown voltage. All of these impact the product performance. And they depend, as before, on material selection, on deposition technology selection, and your deposition environment integrity, so your vacuum quality. The extrinsic film properties, as previously, also depend on uniformity related, repeatability, deposition rate, throughput, and these impact cost of ownership. And as before, they depend on technology selection, the system design, and also the system quality. So let's go through an example of what metallization coating, how does the decision process made for the technology and configuration selection. Let's take a look at the scenario for metallization layers for a high power laser bar. The coating requirements in this case would be low contact resistance, and a key requirement would be the ability to sustain very high current densities. Going to the next step and identifying a critical intrinsic and extrinsic film characteristics, we can say that we will need high density and low defect, low sheet resistance metal layers. We will need multiple material stacks. We'll need co-deposited materials, as we have seen in the case of a gallium arsenide material system. And we also have to keep in mind that we need to deposit on backside thin substrates. So how do these film characteristics translate into technology and configuration characteristics? So high density material, low defect density, we would need to go to a more higher quality deposition, such as magnetron sputtering. We would also need load lock and premium pumping system to keep the defects and the sheet resistance low. We'll need a RF bias stage for pre-clean and maybe some additional film enhancements. And we might need a higher temperature for higher film quality. To address the multiple material stack, we'll need multiple cathodes with different targets. For deposition of co-deposition of multiple materials in the same layer, we will need multiple cathode power supplies, so we can deposit from two cathodes at the same time or more. Low contact resistance, we might have to go with an ion source to pre-clean our substrate right prior to deposition in situ. And then, of course, we'll need specialized wafer handling to be able to hold these 70 to 90 micron thick substrates. So what can we learn from our exercises? What are the advantages of the application-specific process equipment selection, and what is the difference between calculating the factory ROI versus the tool ROI approach in the device manufacturing? But before we answer this question, let's ask you the final question of this webinar. So again, if you can go back to your pop-up window, what obstacles hinder your focus on the system performance? For example, film properties, throughput, uptime, and do select everything that applies. Is it the budgetary restriction? Is it the lack of awareness of alternatives? Is it the desire to keep the process requirements highly confidential so you cannot share with your supplier? Or is it the ability to specify detailed hardware attributes to meet process requirements? Please take your time and answer these questions, and we'll get back to the presentation in a minute. If you have any questions, meanwhile, while we're going through the presentation, please submit them through the Ask a Question box, and we'll answer them at the end of the session. All right, so let's move on. Thank you for your feedback. Let's draw some parallels between microelectronics world and semiconductor laser world. What can we say? The market size for semi is 350 billion. For semiconductor lasers, it's only 5. The spending on the capital equipment for the physical vapor deposition for a semiconductor microelectronics is about 3 billion, according to BCC reports, with many identical tools per fab, literally on the order of hundreds. For the semi-laser world, the capital equipment on expenditure on the deposition systems is about 200 million, according to Denton estimates, with 1 to few similar tools per fab. The industry supported the process development plan for semiconductor industry, for microelectronics, is a single industry-supported roadmap. For semi-lasers, it's individual per company, tightly held, very specific, with very little interaction between manufacturers. We see these trends both in semiconductor world and LED world, where an industry would start with very fractured, very proprietary information with very different objectives. And over time, there would be some consolidation, some similar roadmaps, and also change in behavior with their suppliers. The capital equipment requirements in semiconductor microelectronics worlds, the vendor defines what the hardware should be to meet the process of film specifications. In semi-laser world, we see more often that the customer defines both the process and the film, and more importantly, the hardware. The vendor support, which relates to uptime. The response time in semi-microelectronics world is within hours, sometimes minutes. We have dedicated on-site service engineers. In semi-lasers, the response time is variable. Service engineers might not even be local. And this is related to our final bullet, the number of vendors in the industry. So semiconductors have about 4 to 6 major players, depending on which of these players you ask. The semi-laser is much more fragmented. The number of vendors is over 20. So what can the laser manufacturers learn from the microelectronic industry? Specifically, how is this learning related to the process equipment selection and configuration? Well, let's look at the parallels. First, let's go with the hardware-specific configuration. Many engineers in the laser world specify hardware first. What kind of deposition technology would they want to use? What kind of sources? Sometimes which vendors for these sources do they want to use, and so on, highly detailed. The vendor is viewed in this case as merely an integrator. And it does work for many simple applications or for R&D purposes, but it's not great if this is a key process step in your manufacturing flow. So in the end, what you get is really functional hardware. On the other hand, if you go to application-specific configurations, you have carefully selected capital equipment vendors that have experience with the same or very similar applications across multiple customers. The vendor in this case is viewed as a collaborator, a partner with a standard product addressing key requirements. So here, as a laser manufacturer, you would specify film requirements first, which is what you ideally should care more about. It allows both you and your customers to benefit from vendors' experience, and the vendors addressing multiple customers with similar applications should be able to draw on experience from all of them. So in the end, the result would be a working production process rather than functional hardware. And hopefully, with this observation in mind, let's take a bird's eye view and discuss the factory ROI, the return on investment. Each factory typically requires a small number of tools for each process step. And specifying different vendors for each step might make sense on a film level. For example, you have vendor A who's perceived as best-in-class in optical coatings, while vendor B is perceived as best-in-class in metallization. However, there are points to consider beyond merely film level thinking. By using many vendors, customer is responsible for the entire manufacturing process flow. So laser manufacturer is responsible for the entire process flow. And both vendors A and B do not really have any insight into how their individual tools integrate into the entire process flow. But by partnering with few vendors, vendors can have a better understanding of the entire factory and the process flow requirements. That means that the integration will be typically improved. There will also be faster production qualification. You can realize better service response because the same service engineers would be able to address multiple tools, and there is an incentive to have a service engineer closer to multiple tool locations. We will also minimize operator training costs since tools will have similar look and feel. And in the end, all of this will result in a higher factory uptime. So what is our takeaway in all of this? In order to maximize the factory ROI, do choose process technology that best meets your production requirements. But do not buy more capability than you need just because it's better or top of the line or the highest, the most flexible. But also do not buy less capability because you need it to be cheaper. You have to consider calculations of the cost of ownership rather than capital expenses. And do, in the end, partner with the fewest number of carefully selected vendors to improve overall factory uptime and time to market. And this would conclude our presentation. Thank you very much for your time and attention. And if you have any questions, please submit them in your question box. Thank you.
Okay, Alex, thank you very much. We do have a large number of questions here already, so we'll get to as many as we can. And we will answer all the questions by email if we don't have time to get to them in the next 15 minutes or so. So Alex, here's one on the deposition technology. Where would MBE fit in the table of PVD deposition technologies?
So MBE is typically used similar to MOVPE or MOCVD for active layer deposition. You can get very high quality materials. It is somewhat of a slower technology, but again, if you need very sophisticated active layer stacks, MBE would typically go into that slot in the manufacturing process.
And then another equipment-related question: are there any ALD applications that we know of in
Not that we're aware of.
In the laser industry?
No, not that we're aware of. Although ALD is a very nifty technology, the deposition rates are typically just too low for high-volume manufacturing.
Is that considered to be a future process for semiconductor laser? Is another question on ALD.
It's difficult to say, but we don't believe so. Again, the limitations of the technology are such that we don't see any significant improvements in the throughput or complexity or cost to justify the introduction of ALD into laser manufacturing.
Well, here's an interesting one. This is typical of many requests we get. What type of coating method is your selection for coating of a resonator mirror in a CW high-power thin disk laser? I note that there's very few specifics in there. So we would need a little more information, I think,
Yeah,
to be your answer.
I think so. Again, it depends on what are the requirements for the film. The structure, again, it sounds very sophisticated, but we'll probably need to consider, just as we mentioned in the webinar presentation, you would need to consider all of the final output film requirements to be able to answer the question correctly. But we would be glad to look at it offline.
Just to note, Alex has been giving this talk, but we don't have a selection guide with checkpoints for answering these type of questions. It takes a team of engineers and decades of experience to come up with quick answers to these kind of questions. So it's not an easy one to answer on the fly. Here's one on OMS. Are OMS systems ellipsometry-based, reflectometry-based, or some other technique?
It depends on the setup. Usually reflectometry, so you would have a source, a light source that would be directed towards either your substrate or towards the witness crystal, and you would get the signal back, the feedback reflected light back. I could envision in some cases, in case of transparent substrates, in transparent films, it's possible to have transmission, but most likely it is reflection-based measurement.
Here's another one that just came in. Are there any comments you can make on the purity requirements of the thin films, and is that a major consideration? We talked about 3 different kinds of films here. Maybe there's a difference between the 3.
So for AR/HR coatings, one of the important attributes is their lower refractive index shift, which is related to the moisture content in the films. What this again relates to is what is your defect density, how good your vacuum system is, how little contamination do you see in your films. For metallization layers, it would be also oxide moisture related. Also, it would be related to the quality of your sources. So how good are your targets, or how good are your evaporant sources? All of these relate directly to sheet resistance. Pre-cleaning process would relate to your contact resistance. Hopefully that answers the question.
Here's one that maybe I'll take a stab at. Is the semiconductor laser market size expected to grow more rapidly due to the automotive industry? That is definitely one of the drivers. If automotive headlights are a huge potential market for semiconductor lasers, the LEDs are a competing technology there. The highest end, highest brightness lasers are more electrically efficient than LEDs at the higher current levels, and you can get more directed light. So it's a possibility. You'll see those starting to appear in higher end cars, but I think that's quite a ways down quite a few years out before we know the definitive answer to that. Let's see, what else do we have that's interesting here? Do the high-stress coating methods deform the base material? And if so, what is done to compensate for the deformation? So stress control.
So stress control is a very challenging topic. For high number of layer stacks, it has to do with the stack design. There are possibilities of controlling stress with deposition on the opposite side of the substrate to kind of reduce the overall stress level. But these have to do, some deposition technology like IBS, ion beam deposition would be more, you would have in the end more stressed films. But also, again, film design or stack design in this case would play a significant role.
disappeared.
And just to add to that, the stress, whether it impacts the layers, so if highly stressed films can suffer eventually delamination. So this is the failure mechanism for a laser diode where stress is not controlled.
Okay, thank you, Alex. So here's any recommendations on cleaning before deposition or pretreatments. For example, what is a good process before IBS, ion beam sputtering, for best quality?
So typically, if there is any masking involved, you would want to ash away the remaining photoresist off the surface. You would like to etch off the oxide. You can either do with the assistance of an ion source or chemically, or both. For metallization layers, it's the same. The oxide removal, it's very critical. And it's usually, ideally in situ is best than ex situ, although we do see some applications where an edge followed by, within a few minute deposition is sufficient, but for really low resistance metal contacts, you want to do any pre-clean in situ.
Okay, here's another one for you. For metal deposition, how much does the metal quality, K or absorption or conductivity, change if you go from one deposition technique to another? For example, E-beam to sputtering, and if you change the process parameter, for example, substrate temperature. So substrate temperature and deposition technology impact on the metal film quality.
Sure. So substrate temperature would always help with the higher film quality. Typically, limitations are on the temperature have to do more with the whole process integration, whether you have any thermal budget. For example, photoresist or your active layers cannot withstand the temperature, but high temperature typically leads to better film quality. Sputtering processes in general result in much denser films than evaporation, so here you would inherently have better material. There are ways of increasing the density of the evaporated films, both E-beam and thermal, with ion assist, so ion-assisted deposition with an ion source, in situ ion source. However, these still are somewhat subpar to the sputtering.
Okay, thank you. I did see one question earlier that would be for me on are the slides available for download? We will send you an email, everybody that was registered, with how to obtain the slides. We will be providing those, so we'll be in touch with you after the webinar. Here's another one for you, Alex. So again, this is another good example of the kind of questions we sometimes get. What materials are recommended for low stress?
Again, this depends more on the whole device structure rather than individual materials. So, just like with growing the active layers on a different substrate, as I mentioned in one of my slides, maybe we can go back to that.
Which slide?
The heteroepitaxy slide. Yeah, so if we look at this, the first layers after the substrate are the transition layers, and these are for stress control. So here it's not just about an individual layer that you're growing, but how it relates to the entire stack, where the two defining layers here is substrate itself and the active layer. So that whatever mismatch there is, the stress you want to reduce with the specially designed transition layers. And these are typically very complicated and highly proprietary. But yes, in general, stress control is not due to individual layers, but more towards the whole stack. Although it's true that some deposition technologies result in more, in higher stress films like IBS. There are ways of reducing stress, so we have known that ion assist can, in some cases, reduce stress in the films, but the primary driver is the overall stack design.
We got a follow-up question on the metal quality. Can we quantify how much the metal quality changes?
Yes, maybe we can follow up offline and send out any information that we have.
Yeah, that's kind of detailed that's fairly detailed and specific, and would impact would depend on the exact parameters chosen. So not an easy question to answer generally. Let's see if there's any other of these I want to answer. I think we're running out of time and questions here. Here's a question. Is Denton Vacuum able to support engineering of equipment to meet specific deposited materials requirements?
Yes. The short answer is yes.
I hope that wasn't our boss who just asked that, right? But yes, that's one of the things we do. We do take our platforms that are designed to meet a large number of requirements and apply them to your specific requirements. So Tammy, I think we're about done with our questions.
Okay, great. Well, great job, guys. Thank you very much. And on behalf of Laser Focus World and Penwell Corporation, I'd love to thank today's speakers, Alex Manison and David Douglas, who joined us for the Q&A, and our sponsor, Denton Vacuum. This presentation will be archived within 24 hours and can be reached from our homepage at laserfocusworld.com. A reminder email message will be sent to all registrants, complete with a link to the archive. And we want to thank you for joining us today, and we look forward to bringing you more webcasts in the near future. Have a great day, everyone.
Thank you.